I'll show, all mechanical paradoxes, most of them are either perpetuum mobile, something that breaks the conservation of energy, or like we call it Münchhausen machine. Münchhausen, the guy who pulled himself out of the swamp by his hair. Its Münchhausen machine is something that breaks the conservation of momentum. What I'm going to do, and of course there's the second order perpetuum mobile breaks the second law of thermodynamics. What I'm going to do is this. I'll formulate some paradox that clearly breaks all physics we know, and your job will be to debug it. So if you can show me where I made the mistake, and not just say, no, you're wrong, this is not, you don't do physics like that, it should be done differently. If you can pinpoint my mistake, you raise your hand, and then someone else raises his hand when he gets it, and then there's this third guy.
And then I'll just be sitting here waiting for someone to
The third guy will get the permission to speak. And when I convince him that he is still wrong, then we will continue until we solve it. If you don't solve it in 5 minutes, I'll just do the solution, and we proceed to the next one. Okay? So I'll start with the really simple ones, and then we will move forward. Okay. Story number, of course, and here we will have a table of grades. You after you solve it, you rank it from 0 to 10, and we'll see which is the best one, which Australian team liked the most. Okay, so let's start with number 1. I have a car. How do you draw a car? Well, it is almost a car. Car goes with velocity v in this direction, and at some point the driver hits the brakes, and the whole of kinetic energy of the car is dissipated into heat. Kinetic energy becomes 0, and heat becomes Q, which is obviously equal to the kinetic energy the car had before the whole thing happened. Okay, so far so good, right? Story number 2. I have a car which goes with velocity v, but actually it goes with velocity 0 from the point of view of this guy, who is sitting in an inertial reference frame, also going with velocity v. Then suddenly the driver hits the brakes. We have the car that whoosh accelerated away, that suddenly got kinetic energy half mv squared, and also released the heat. Okay? Now we have both the heat and kinetic energy. We had 0, and we now have them both. So the energy conservation clearly breaks here. Where did I lie? I'll remind you that if you want to pinpoint a mistake, you have to raise your hand. Okay, we have 1.
Do any of you have any idea?
You can think, you can compute things.
Has it got to do with inertial reference frames and what happens when it's sent to the brakes?
Yeah, this of course, this is not a frame of reference of the car. This is an inertial frame which continues moving with constant velocity.
Is there any work being done on this thing?
Sorry?
Is there work being done on the thing?
Work?
Yeah.
What do you mean work? I'm not sure what work really is. I'm just doing simple things. I know one thing, that if you compute an energy in one state of the system and you compute the energy in the other state of the system, it should be equal. No matter what manifold of changes the system undergoes. Like Richard Feynman said, it's like a black knight in chess. You know that whatever it is doing, it will remain black. Because this is how it works.
It's what you going to
Well, I was going to say, could it be, you've got the ground moving with...
Oh, you have the ground moving, but the ground is really, really heavy. The ground doesn't change its velocity too much.
Yeah.
Well, you know what? Here we also have the ground moving, so what here we had no problem.
Well, in the first frame, we're in the frame of reference of the ground. Whereas in the other one, we're in the frame of reference of the person, so the ground's moving backwards at velocity v. And so when there's friction between the ground and the car...
Okay, you want to talk to me about the ground. The ground was here and it made no problem. The ground was here and they say, here it will make a difference, while here it didn't. Okay, you know what? I will agree with you and we are going to compute. Let's assume that the ground is something infinitely heavy, it has infinite mass. And its energy, kinetic energy of the ground, will be of course equal to infinite mass times velocity of the ground squared over 2, right? Or we will write it in a more convenient form, like huge momentum of the ground, really infinite, over 2m. Let's approximate, and as please remind me your name?
Chris.
Chris. As Chris suggested, we will try to approximate the change in this infinite energy. So the change, we all like doing linear approximations or approximation in general because physicists are lazy, would be of course 2p change in p over 2m. The change in the momentum is of course the momentum of the car. So it's mass of the car times v of the car, which is of course the change in car's velocity. 2 we can get out of here, and p over m, p ground over m ground, both infinite, but the ratio is of course the velocity. So we have v times as I promised mv of the car. Haha, we found the mv squared, which is the change of the ground's velocity, ground's energy. If ground's velocity is 0 like it is here, the change is 0. But if it is not 0 in the beginning, there is this change, and of course mv squared accounts both for half mv squared of the kinetic energy we obtained and half mv squared of the heat we obtained, and everything is fantastic. Okay, thank you Chris for solving this one for us. How do you rate this paradox? Not paradox anymore?
5 points to Chris and 5 points to Pavel. Huh?
No, we just graded based on how fun it was.
Yeah,
We have nothing to compare it to.
You have nothing to compare. Okay, so you give it 0. Okay. I'll try another one. Round table. No, it's not a round table, but it has a round, very smallish hole. Well, this is not a smallish hole. Let's use Slava's trick to erase it.
You'll put it down properly.
Sorry. This is table. You believe me, it has legs, but I want a smallish hole through which there is a rope that goes under the table and it goes also behind. Eventually it gets through this hole. The screen should be properly aligned, and there is a ball here of mass m, which is spinning with velocity v. of course, to have this whole thing happen, there's no friction. You need to fold it with force F, which is equal to what? mv squared over r, right? And now I am going to pull it. This is my hand. I am going to pull it down. What will happen to the ball? What is conserved? Angular momentum. So it will accelerate, right? What is angular momentum? It's mvr. It's like regular momentum times r, right? So if v dot r is conserved, so mvr is conserved, but it is equal to L, and it's equal to constant, then v equals v0 r0 over r. So when the r is getting really small, velocity really explodes. Where is the energy coming from? I am doing mechanical work, obviously, when I'm pulling this against this force. Everything is fair and square. And now, there is a surprise. Now I have the same table, and have a really thin stick coming out of the table, and the ball, and the rope which is wound around this stick. Nobody is holding anything. As the ball moves, it gets wound around the stick, the pole, and this distance decreases. Since the angular momentum is conserved, we are of course getting the same thing, and it constantly accelerates, getting its energy out of nowhere. And well, of course, you can make sophisticated machinery out of this, which makes energy out of nothing. You just accelerate a ball, put it on the table, make it wound around something, and it will accelerate all by itself. Very nice, isn't it? Do you buy it? I remind you to raise your hand if you can points by times will this. Searching for.
In the second situation, the ball will move inwards. I think it'll
You
just,
don't think it will accelerate, but
I think it'll just unwind itself and fly off the table.
well, it's like the rope is really strong.
But it's not attached to the stick, it's just wound. Like, is it just wound around or is it knotted to the stick?
If you know sailing, you should know that if you wind things around the stick, it can be really strong.
Yeah, but I think it'll unwind itself.
You know, wind itself. Why? How? You know what?
It's been the other way. Yeah.
Let me suggest a deal. I will take this end of the rope and I will glue it with super glue, which is really strong, to the stick. And I will really force it to wind itself. And it will indeed accelerate. There's no change to the Earth's kinetic energy like we have seen from the previous one, because if the Earth is not moving in this reference frame, its energy change is going to be negligible. Okay, the previous trick is not going to work. So what's the story?
Oh, in the second one, the table rotates. Was it?
No, the table is also super glued to the ground. And the floor is part of the building constructed. Eventually, the whole thing is one big structure together with the Earth, and it has infinite mass. Should I give you 5 minutes?
When the mass is a long distance away, it has some rotational kinetic energy, half I omega squared. And then
Please say again.
when it's a long distance, it has rotational kinetic energy, half I omega
This has rotational kinetic energy.
Yeah.
No, it doesn't. It only has regular kinetic energy. It is moving with velocity v. I neglect the rotation of the spinning of the mass around its own center. Well, of course you can count this whole kinetic energy as rotational about this.
Yeah, so then when it winds around, the moment of inertia becomes smaller, so it would make sense that omega squared would increase.
Omega square would increase.
So the angle, so the...
But also v would increase. You agree with me that I didn't consider rotational energies. I only considered mv squared. And if m is constant, v is increasing. You agree with me that v is increasing, right? Then the energy would increase. And the total energy of the system is surely the kinetic energy of whatever has mass here, and it's just this small. Should I solve this one for you? No, you know what?
John, you have any ideas?
Huh? I think you guys just so tired after a very long day. I also had a long day, but I didn't study physics. Bye.
Maybe Nick's right. Maybe the velocity doesn't actually change.
The what?
The velocity of the ball doesn't actually change because it's parts of the
That's not what Nick said.
Maybe it appears to change, but it doesn't actually
Yeah,
change.
it
You say that
spins
the
around.
velocity is not going to change,
No,
why not?
it spins around faster. So it's making more circles in the same amount of time.
Yeah, but we clearly computed that the velocity is going to change. You know, this is the velocity and it depends on the radius. It's a constant, or 0 times v0 divided by radius. Radius is changing. And as we said, the angular momentum is conserved. It is going to accelerate.
This is like the last question where the ground does something.
No, I told you, ground is not going to do anything here. Because we computed the energy change of the ground. You give it momentum, then nothing happens in the reference frame in which it didn't move in the first place.
Would the ball oscillate?
Huh? Sorry?
In the first case. Yeah.
A slight line.
I don't know, just got a feeling.
We've done this question.
go.
It was one of those mafia questions.
Yeah.
Perfectly frictionless stable or something.
Is it to do with the tension in the string?
Tension of the string.
Yeah.
Well, if the string is perfect, if it's not a spring or something, then its energy doesn't change, doesn't depend on the force. For a spring, it would be, of course, half kx squared, or you can also express it with force. It will be for a spring that is stretched with force F, it's F squared over 2k. But if it is really, really hard, if k is infinite, then the energy of this rope is not a part of the system. No comments on the previous one? Still no solution? Okay, come on. This is the floor now. This is the floor. Here we have a whole bunch of rope. And here we have a pulley. Well, my drawing is not so good. And the rope goes down to this side. And this is the system. No friction whatsoever. The rope will move down. And eventually all of the rope will be found on the right side. Yeah, this cannot be stable. This is not equilibrium. What can be though, and here you are going to believe me, because I never lie, at least I'm not going to lie this time, that this thing can move with constant velocity. This is a possible solution. It is not going to accelerate. Why is it not going to accelerate? You know, this part has a mass, and there is a force on the rope, so why it's not going to accelerate is actually an interesting question to discuss, which we won't. But it is related to the fact that it is not a real physical body. It's not like I put constant force on this bottle. It is force applied onto different parts of rope every time. So the solution with constant velocity is actually possible. For now, you are going to believe me that there is a solution with constant velocity. Actually, though, it will reach, if you start it from rest, it will reach this velocity asymptotically. If you start it with constant velocity, it will just continue. If you move it faster, it will go down to this asymptotical velocity. And I'm going to compute this velocity in two ways. One using energy conservation, and another using momentum conservation. And then we'll see which one beats the other. Okay, energy. How would you do that from energy? First, is the energy conserved?
Yes.
Yeah, it should, right? But we have a whole bunch of rope here, and it then finds itself there, so the potential energy clearly changes. And this is at rest, so all mechanical energy really changes. It is converted into heat, right? Where does the heat come from? Heat is here. Rope with velocity v impacts the floor, so the whole of kinetic energy of the rope is converted into heat. How much heat are we going to have at the end? Heat cubed. We are going to have as much heat as the decrease of the total potential energy of the rope, right? It is m. This height will be h. Okay? Velocity here is v. And the total change in potential energy is m times h times g. Right? This is, of course, equal to the kinetic energy the rope had just before hitting the wall, where this heat was created. So it is equal to the total kinetic energy of the... It doesn't matter that different parts of this chain hit the floor at different times. We can just say that the total energy is total mass times half v squared. Right? This kinetic energy, should be equal to the heat. What we have from here? We have the impact velocity, of course, which is, of course, the velocity of the movement of the rope. Yeah, we assume that there's a lot of rope, and well, the system operates for a long time, and the velocity of the impact is the velocity of the rope. So velocity becomes do you know this number from somewhere? Is it familiar to you? It is this. It is the velocity of the falling object from height a. Is it okay? So far so good. Let's compute it differently. I am now going to use momentum. What is the total force? What is the total force? I will take some different color. Pulling the rope at this place. The force that is used to bring more and more parts of the chain into this game. What is the force? Well, of course, this part is moving with constant velocity. So whatever force is here, pulling down, will be the same one as here. And this force is, of course, the weight of this part. So the force accelerating new parts of the chain is equal to mass of this thing times g. It's small m, right? It's not the mass of the whole bunch of the rope. It's just mg, and of course mg can be expressed as the mass density, linear mass density lambda times h times g. Right? What is this force doing? It is of course bringing more and more momentum into the system. What is the momentum of the small part of the rope? Let's small part of the rope, it has small momentum, so we will denote it as dp is of course mv, right? It's velocity of the new element. This is the new element which is going to rise into the air times little mass. What is the little mass equal to? It is the linear density times the length. Let's call it lambda v dx. Right? Okay. And all this happens in small time dt. In small time dt, how much momentum does, how much impulse does this force bring into the system? It is of course f times dt, or lambda h g times dt. Is it all clear? Do you agree with that computation? Does everybody agree? Anybody has any question? I am going to confuse you with it now, so it is time to ask a question if it is perfectly clear. If this is 100% correct, and you 100% agree with it. Let's compare these two parts and divide everything by dt. dx over dt is what? The velocity, v, of course. You already see the answer, right? V equals square root of gh. Lambda falls out. Dx over dt we have v squared. That's it. So which one is correct? What type of a paradox is this? Is it a perpetuum mobile or is it a Munchausen machine? Is the energy computation correct? Or is it momentum computation? Which of the basic laws win?